Well, good morning or afternoon or evening, depending on when you are actually listening to this. So, today we are going to be talking about the scientific method and kind of why scientists are required to follow a set sort of procedure. Okay? So, first thing I want you to think about is just how many things in life do we have a set procedure that we have to follow? Think about driving. All of you guys are starting to get to that age where you're itching to get your temps. And if you don't know that that red octagon means stop, you can get a ticket. You know you have to drive down the right side of the road, right? Because then we're able to have a very organized universe system. It's just like when we're driving in Ohio versus driving in Michigan, the speed limit is still going to be in terms of miles per hour. Now, when you go to Canada, it's in a different system. It's in kilometers per hour. So when we're looking at systems, we want to make sure everything is kept the same. Same exact reason why horses used to be said that they were 13 hands tall. Well, if you look at your hand and you consider the hand of your mom or your dad, we all have different sized hands. So if somebody has really small hands, they're going to have a super tall horse because they'll get more hands, right? So we started creating all these systems and ways to make sure that things are kept the same, that they are uniform, so that we actually have scientists and doctors that are doing research studies that can come out with evidence that we can trust, right? You don't want to all of a sudden get told that if you drink a ton of Mountain Dew every single day, at least 1 gallon, that you'll be immune from ever catching a cold, right? So we would need to actually test that to see if that's an actual thing. So sometimes when you guys are reading on the internet or looking at things on social media, you really have to consider, okay, where is this information coming from? Is this an actual scientific study that's saying this is a possible solution to whatever problem you're considering? Or is this just somebody that's blowing smoke? Because sometimes we just don't know. All right, so the scientific method, I am sure you guys have talked about the scientific method in every single science class that you have ever had, okay? In that scientific method, we're going to be able to identify a problem, something that is occurring. And so we're going to see this happening and decide, there has to be a way to fix this, right? So when we observe something, we're going to observe something through our senses. And we're going to say, okay, I just saw this happen, or I'm smelling this, or I touched this object and I feel this, right? Those are all of our senses. And then we're going to come up with a hypothesis. And a hypothesis is going to be an educated guess, typically written as an if-then statement. So if I give my plants more water, then they will grow more. We then want to actually test it out. And in order to create a nice, valid experiment, there's certain things that we have to keep the same. And then there's going to be one variable that we actually want to change. We then are going to go ahead, collect some data, analyze that data, and then form a conclusion. If our conclusion does not support what we had initially thought in our hypothesis, that doesn't mean that we're done and we failed. No, we actually learn and we go on and we retest, right? Think of Thomas Edison. How many light bulbs did he go through before he found the perfect one, right? He had 100+ trials till he found an actual bulb that works and is able to produce light. So even if you fail, and I want to use that fail in quotations, I wish you guys were here to see it, you're not actually failing. You're actually gaining a better understanding of the problem and identifying that that variable is not affecting it in the way that you believe. All right, so again, those observations, those are things you gain through your senses. A scientist is going to notice something from the natural world. Okay, so those observations have to come first. An observation might be something like seeing that a salamander has curved, not straight tails. Right? So we're starting to identify, there's been some change in this population of salamanders when really, ideally, they should have those straight tails, right? This one you might be like, whatever, like not a big deal. But when you start thinking through why there might have been that anatomical change, you might start thinking about, well, what has changed in the salamander's environments. Is there a new pollutant? Is there a change in their diet? Is there a new predator? And you have to consider, if there's a pollutant or something in the water, well, who's also drinking that water, right? A lot of our livestock get water from fresh sources, right? We get our water from groundwater, from sources. So when we look at that, ultimately, there's going to be some way that it's going to come back and impact us. So once we have identified that problem and we've observed something happening in the natural world, we want to try to come up with a hypothesis. The key thing is that it has to be testable. So that means that if I want to see what's going to make my sunflowers grow taller, I could test that. If I want to see how to make the earth spin faster, I may not be able to actually test that, right? So I got to be careful when I start thinking about a problem that I want to address. Is there a scientific solution? Is there something that we can do that we can then test and observe the results? Okay. Typically, things get written as if-then statements. And that then is the prediction. That's your outcome. So you're starting to anticipate sort of what is to come. So when you start seeing something, you know what you want your desired result to be. I want to have nice, tall sunflowers. Well, in order to have nice, tall sunflowers, I probably have to give it something like water, fertilizer, sunlight, in order to allow for it to actually grow. So I can't change all three of those things, but I can change one. Okay, so I might say, I think sunlight impacts the growth of the sunflower the most. So my hypothesis might be, if a sunflower receives more sunlight, then it will be taller. So I'm going to change the amount of sunlight, and then I can record and measure the actual height of the plant each and every single day. So again, here's another one that comes back with the salamanders. If the salamanders have curved tails, then that is caused due to a pollutant in the moist soil or the water where they live. So again, that experiment part of this then is to create a procedure. A procedure is very detailed, step by step. So if I said, teach me how to make a PB&J sandwich, you would have to be very, very explicit and say, remove 2 pieces of bread from a bag. Lay the pieces of bread flat on the table. Remove the lid from the peanut butter jar. Take a tablespoon of peanut butter and smear it on one side of the bread. And then I would continue that. So do you see how that is very step by step? There's no room for guessing, right? I wouldn't say just put some peanut butter on the bread, because I don't know about you, I don't like a lot of peanut butter on my PB&Js, because then your mouth gets real dry and sticky, and then it's like you can't even chew, and then you're dying for water, and it never works out, right? So each person can interpret something differently. So when we're looking at procedures, it has to be very, very explicit. And you have to make sure that it's in a step-by-step process. So that is part of your experiment. In your experiment, you're going to have variables. Those variables are factors that are going to affect the outcome. So your variables, we want to make sure we're only changing one thing. Because if I take my sunflower and I give it varying amounts of water, fertilizer, and sunlight all the different times, then it's really difficult for me to measure that and to say, I know for sure water had the greatest impact, because you can't anymore. When you're comparing it to other sunflowers, if you change 3 different things, it's not gonna be a valid experiment. All right, so again, in order to be a valid experiment, you have to only have one variable. This variable that you change is our independent variable. So take a look at this example. Sarah's learning how to drive and really wants to determine how fast she can go in 10 seconds. She thinks the car will go faster if she has bigger tires. So on Monday, Sarah tries 3 different tire sizes. On Tuesday, Sarah tries 3 different brands of tires. And then on Wednesday, Sarah repeats Tuesday's test, but today it's raining. So I want you to think about what makes a car accelerate and go fast. Okay, we will do physics the second semester, so looking at friction is important when we look at contact between tires and the treads and the ground for it to actually turn. If you consider different cars, a semi is a lot bigger than, say, a Prius. So a semi is not going to speed up as quickly. So there's a lot of different factors that can change and that will impact whether or not the car will go really fast. So when I look at this, again, in order for it to be a valid experiment, we said we can only change, do you guys remember? One variable. And this one variable is what we call the independent. That independent variable is the one thing that we think is going to attribute the speed to change. So she thinks that it's the bigger tires. So if she thinks bigger tires are going to change how fast she goes, should she change out the brands? Hopefully you're saying no. Should she change other factors like whether the ground is wet or dry? No, right? It's okay that she had different tire sizes. That's exactly what she is testing here. But I can't test 1, 2, 3 different things and be able to say for certain, this is how I can drive faster. This is how I can speed up and go quicker, right? So for this one, it is not a valid experiment because we have too many variables, too many things that are changed. All right, so again, we have scientists. Those scientists are going to follow very strict rules, making sure they're only changing one specific factor, and they want to see what the outcome is because of that factor. So again, if I change the amount of water I give my plant, the end all result might be the plant is taller, or maybe it produces more flowers, but I got to pick what I'm actually going to measure. Okay. Again, with that, we also said the procedure should be very detailed, very precise, because for it to be a good experiment, it's going to get shared with other scientists around the world, and they're going to try to replicate it. All right, so again, control variables. We talked about the independent and the dependent. Independent is what you are going to change. Dependent is what you're going to measure. And then the control variables are everything else that's kept the same. So let's go back to my sunflower example that I keep talking about. All right, here's my beautiful sunflower. Okay, I have 3 sunflowers. Doop, doop, doop. They are all outside in Miss Baker's backyard. Because they're out in Miss Baker's backyard, do you agree the soil's the same? Yep. So I have the same soil. I have the same location. I have the same amount of sunshine. Okay. I have the same type of plant. All right, it's not fair to compare tulips to sunflowers. I mean, sunflowers are giant, tulips are pretty small. Okay, so I'm going to keep all those things the same, but I'm going to give this flower 5 milliliters of water. I'm going to give this flower 10 milliliters of water. And then I'm going to leave this one over here to only water that comes from the rain, so from the natural sources. So this would be our regular conditions. Okay, I might actually add on here 2, 3 flower comparisons. We might need some more, so maybe here I'll have 15 milliliters. Here I might have 20 milliliters. Okay, just so I get a little bit bigger of a data pool. We never want to have very, very few data points. We want to have a lot more. We might also do this multiple times. So if we want to, we can repeat this over and over and over, still only changing that one variable, which would be our amount of water, keeping everything else the same. Being tested. So come back here, we're not testing the soil. We're not testing changing the location. We're not testing changing the amount of sunshine or the type of plant. All right, again, with the controls, that's what's not. Okay, So again, controls not being tested, that's what we keep the same. So again, independent variable, this is what is changed. Dependent variable, this is what we're going to measure. So I change the amount of water, and I'm measuring the height. All right, so again, here's another example for you. Let's say maybe you didn't go to Bradley, you actually went to Darby. There's a lot of houses around Darby, not a lot of houses here, right? So let's say that you want to walk home and you want to find the fastest route. So you're going to take different routes. So let's say here's my school, and here's my house. We'll make my house way smaller than school. And I can either go route 1, which is like this. I could go route 2, which goes around. And maybe I can go route 3, which is just a straight line. So I have 3 different routes. All right, so let's think about it. So we want to figure out which route is fastest. So I'm going to have different routes. The different routes is my independent variable. What I need to keep the same then would be the person who's walking, which would be me or you. I want to keep the pace at which I walk the same, because that's not fair if you and your friend try to race home and one person walks and the other person runs. Well, the person who runs is going to win every time, right? So I'm going to keep that the same. I'm going to keep the start and end position also the same. And I also want to keep the other environmental factors the same. For example, if walking home on Monday, I take route 1, and on Monday it's nice, it's sunny, there's no wind. But on day 3, so Wednesday, I walk home on path 3, and there's a ton of wind in my face. Well, I know wind's going to slow me down, and it's going to make it a lot harder to get home. So I want to try to replicate similar environmental conditions as well. All right, so independent variable, what I changed is the route. The dependent variable, what I'm going to measure is the time it takes to get home. And then the control variables, again, these are all the things that I'm going to keep the same. All right, so again, there you go. There's it again. So again, it might take several trials. So if we come back to our houses, we might do route 1 3 times and then get the average time that it takes. We'll do route 2 3 times, get the average time it takes. And then route 3, again, average time, see how long it takes. And then we can make a well-informed decision and come up with a conclusion as to which route is actually fastest. All right, again, in order for it to be a valid experiment, remember we said we're only changing one variable, right? We're only changing one factor. Not only that, we also want to try to keep it separate in 2 different groups. Okay, we have control groups and an experimental group. The experimental group is the one with my sunflowers of the different amounts of water. The control group would be my sunflower that received the water from natural sources, also known as when it rains during the day. Okay, so again, one thing that's being changed, so I'll have one group that is the control, one that is the experimental. You guys might know of this one in terms of like medical studies. When we talk about medical studies, you have the groups that receive the actual drug, the new created experimental, yay, life-altering drug that might work to cure cancer. And then there's another group. This one's our experimental, this is our experiment, so this is our control. My control group, they're getting a placebo. So the placebo is actually just a sugar pill. So they're not actually getting the experimental drug. Instead, we're keeping all the conditions the same so that we can actually say, well, in our experimental group, they saw a reduction in the size of the tumors, whereas our control group did not. The tumors actually got bigger. So we'll actually compare between those 2 as well. All right, our data that we are going to get may be quantitative or qualitative. Quantitative, you see how there's an N there? That's because that goes with numbers. Quantity, you probably know that word instead of quantitative. The quantity would be the numbers. So it grew 5 inches. or produced 3 flowers, okay, or shrunk the tumor by 5 centimeters. Qualitative might just be observational. So we could say the tumor got smaller in 5 of the 6 cases. We're not saying how much smaller, but we're saying it got smaller. So when we look at the scans and we analyze it, we can say, okay, qualitatively, this again would be using our senses, I see the tumor is smaller, rather than saying the tumor shrunk by 20%. If I said by 20%, that would be quantitative, whereas qualitative, it got smaller. All right, again, we organize our data typically into charts, tables, or graphs, and we want to publish all of our data. We cannot throw out data and claim human error. If there is human error, you redo it, okay? You would never just say, whoops, I just measured it really poorly. No, you don't take that data. You redo it, right? So no human error there. And then hopefully by the end, once you get all that data, you've analyzed it, you can make a conclusion and determine whether or not your data, your experiment, supports your hypothesis or not. And again, it has to be backed by data. If, though, it does not support it, again, you don't fail. You just retry it, right? Retest it. Look at a different possible solution to your problem, and then see if that gives you the desired results. All right, so again, just to recap, again, we're going to try to identify a problem. That problem that we see is probably gained through our observations, our senses. We then are going to form a hypothesis. Again, this is a prediction. This is the possible solution to a problem. If I do this, then I will observe this. Create an experiment with a procedure that's going to test my hypothesis, collect and analyze my data, and then form my conclusion, and if need be, retest. So that is in a nutshell our scientific method and why we need to go through the process of the scientific method. Again, science has huge implications on our daily life in terms of medicine advancements, new cancer drugs, new chemicals that we're putting on our lawns as fertilizers. In every sort of area of our life, science is at work. Okay, so we want to make sure that people are safe, that the information that people are claiming is true, their hypothesis, when we want to support it. We got to make sure that it is actually backed by science. We can't just come up with something, a conspiracy or some kind of hoax or whatever it may be, and get people to believe it, because it could put people's lives at danger. All right, if you guys have any questions, please, again, let your teacher know, whether you have Miss Tarliff or Miss Baker, and we are here to help you. And we will see you guys tomorrow on Zoom. Have a good one. Bye.